So students, we have seen that whenever a conductor is placed in uniform electric field, or when some charge is given to the conductor, so some properties we have already discussed. So when some charge is given to a conductor, then it would be uniformly distributed on the surface of the conductor. So means we can store charge on the surface of the conductor. We can give the charge to the conductor and it would be uniformly distributed. So this property of a conductor is called capacitance. So what is electrical capacitance? So now let us discuss. The measure of the ability of a conductor to store charge is known as capacitance or capacity. So we have already seen that whenever some charge is given to any conductor, it will go to the outer surface of the conductor. Means we can store the charge on the conductor. So this ability of a conductor is called capacitance or capacity. Now you see, when charge is directly proportional to the potential, or we can say that potential is directly proportional to the charge. Whenever some charge is there, some potential would be associated with that, and that potential is directly proportional to charge, or we can say that charge is directly proportional to the potential, or Q is equal to CV. So proportionality, when we are removing, there is some constant of proportionality, that is C. This is the constant and its name is capacitance, and its value is C is what? This is charge per unit voltage. So if V is equal to 1 volt, then capacitance is equal to charge. So capacitance of a conductor is defined as the charge required to raise its potential through 1 unit. So again, I'm repeating this definition. It's very important. So capacitance of a conductor is defined as the charge which is required to raise its potential through 1 unit. So as you see, capacitance we have already defined. This is the ability of a conductor to store the charge. So how much charge it is requiring to increase its potential by 1 unit. So that ability of any conductor is called its capacitance. So this is the measure of the capacitance of a conductor. So how much charge is required by any conductor to raise its potential by 1 unit. Now SI unit of the capacitance is farad, and capital F is the symbol of the capacitance. And you can see here, this is the symbol of the capacitance. So two parallel equal lines you need to draw when you have to draw the symbol of the capacitance in any electrical circuit. Capacitance is said to be 1 farad when 1 coulomb of charge raises the potential of the conductor by 1 volt. So from this definition we can define the capacitance, 1 farad capacitance. You see, if C is equal to 1, then Q it has to be equal to 1, and V it is also equal to 1 unit. So what we can say here, that capacitance is of 1 farad when 1 coulomb of charge can increase its potential by 1 volt. So then the conductor is said to have 1 farad of the capacitance. Okay. Since 1 coulomb is the big amount of charge, the capacitance will be usually in the range of millifarad, microfarad, nanofarad or picofarad. You see here we have defined 1 farad of the capacitance is what? This is when 1 coulomb of charge is given to a conductor and its potential is raised to 1 volt. Now 1 coulomb charge itself is a very large amount of charge. We know that when you want to give the charge to any of the conductor, you have to give the electrons, you have to transfer the electrons, and 1 electron is having charge only 1.6 into 10 raised to minus 19 coulomb. So 1 coulomb is very large amount of charge. So 1 farad capacitance is very large capacitance, here the practical units of the capacitance are millifarad, microfarad, nanofarad or picofarad. In numericals also you will see millifarad, picofarads, nanofarads. These are the practical units of the capacitance. Now let us see capacitance of an isolated spherical conductor. As we have seen what's the formula of the capacitance. Capacitance is charge per unit potential. So I need to derive the capacitance of isolated spherical conductor. Suppose I'm having a spherical conductor. I want to find out the capacitance of that. Now spherical conductor, let us consider R is the radius of this spherical conductor. And let us consider some charge Q is placed inside the conductor. So I need two things to find out capacitance. One is charge. Charge is already there, that is plus Q. Second thing I want, that is the potential. So I want to find out the potential of this sphere. So I have to see what is the potential of the sphere inside the conductor. So potential would be, simple formula of the potential can be taken, KQ by R. So this is the potential inside the conductor, and capacitance, we are using the formula C is equal to Q over V. So substituting the value of V here, when you will substitute V here, V is Q over 4 pi epsilon naught R. So Q would get cancelled, and this formula of the capacitance we will get for a spherical conductor. Now using this formula, if you know the radius of the spherical conductor, epsilon is what? Epsilon naught is the permittivity of the free space, 4 pi is constant. So you can see here the capacitance is directly proportional to the radius of the conductor. So more is the radius, more would be the capacitance. Epsilon naught is when the conductor is placed in the free space, but if the conductor is placed in any of the medium, then this epsilon naught would be changed with epsilon. Okay, the capacitance of spherical conductor is directly proportional to radius, so we can say dimensions of the conductor. Here it is dependent upon the dimensions of the conductor. Second equation, the above equation is true for conducting spheres, hollow or solid, for both. So the same equation we can use whether it is hollow or solid. So for both of the spheres we can use the formula of the capacitance. Capacitance of spherical conductor is 4 pi epsilon naught R. If the sphere is placed in the medium, then epsilon naught would be replaced with epsilon, and we know that epsilon is epsilon naught into epsilon naught. So we can remind this formula. Epsilon R is what? This is the permittivity of the medium divided by permittivity of the free space. So using this, epsilon can be written as epsilon R into epsilon naught. So this formula is for the spherical conductor when it is placed in the medium. Capacitance of the earth is 711 microfarad. Suppose if you want to find out the capacitance of earth, what you want? You have to simply substitute the radius of the earth here. We know that the radius of earth is 6400 kilometer. So when you will substitute 6400 kilometer here, epsilon naught is 8.854 into 10 raised to minus 12, pi is 3.14 and 4 is there. So substituting all the values here, the capacitance of the earth, that is just 711 microfarad. Micro, we know that it is 10 raised to minus 6. So very small amount of capacitance is there. So 1 farad capacitance, that is why I was telling you 1 farad capacitance is a very large amount of capacitance. So in practical, we have microfarad, picofarad, nanofarads. So this is the capacitance of the earth. Next topic is principle of the capacitance. So we have seen capacitance is what? This is the ability of a conductor to store the charge. Now if any of the conductor is given the charge, some amount of charge can be stored. But if you want to store large amount of charge on any of the conductor, there is a there are some methods by which we can store the charge on a conductor. So let us see what is the principle of the capacitance. Let us consider we are having a plate A positively charged and plate B is neutral. We are having two plates, plate A and B. Plate A is given positive charge and plate B is just neutral. So this charge may be given by induction or conduction method, whichever. So maximum charge is given to this conductor, which is residing only on the outer surface of the conductor. And let us consider we have given the maximum charge to this conductor, and you see when you have given the maximum charge to the conductor, then further addition of the charge on the plate would not be possible, because already it has acquired very large amount of potential. Further any positive charge cannot be placed because of the force of repulsion or very high potential of this plate. And now I am having another plate which is neutral. So some potential difference is there between the two, that is V. Let us consider, so potential is V here, maximum potential. And now when the neutral plate B is brought near A, charges are induced on B such that the side near A is negative and other side would be positive. We know that by induction, electrons will, suppose B is brought nearer to A, then what would happen? The electrons in the B will start moving towards a positive charge. So the side of B which is nearer to A will become negatively charged. It will acquire negative charge, and the side which is away from A would acquire positive charge, because electrons, they have moved from one side to the other side. Now in this condition, the potential is again V. You see, total potential at any point is because of all the charges using superposition principle that we already know. Now the potential due to this negative and this positive is equal and opposite, so it is not going to affect the potential to the large extent. So potential is again V. Now what we can do, we can earth this side of B, and then positive charge will be flowing to the earth and only negative charge will remain here on the plate B. So net potential of the system now will get decreased, because the positive and negative, both of them, they were equal and opposite. So potential due to the induced negative or positive charge on the B was not affecting too much initially. But now when the positive charge of plate B has gone to earth, only negative is left here. So this negative will have negative potential. So total potential now would get decreased, and we can place more charge on the plate A. So here we can say that an additional amount of the charge can be given to plate A in this condition. This means the capacity of storing charges on A increases. So initially what was there? Only one plate A was there, maximum charge was given, and now you see when we have placed one neutral and earthed plate near this plate A, the capacity of A can be increased. So this is the principle of the capacitor. And the two parallel plates, combination of the two parallel plates is called capacitance. So this is one type of the capacitance. We can form another types of the capacitance. Two spherical conductors may be taken, two cylindrical capacitors may be taken to form this type of arrangement. So this is all about the principle of the capacitance.